In this video, I'm going to show you how to Fourier transform a rectangular function. This is a very simple function to Fourier transform, but it has many different applications. In the end of this video, I'm going to use the Fourier transform of a rectangular function to derive the diffraction limit for optics. This is a plot of a rectangular function, which is symmetric around 0. The length of this function is t, and it has non-zero values going from minus t over 2 to t over 2. I will assume that the rectangular function has a constant amplitude of 1. This is the rectangular function in equation form. I'm using the Heaviside function, or the unit step function u, to describe the rectangular function. Here's the definition for the unit step function. Okay, now let's Fourier transform the rectangular function. The key realization that you want to make at this point is that the rectangular function is non-zero valued only between minus t over 2 and t over 2. And inside this range, it has a constant value of 1. This should be a pretty easy integral for you to solve. What we get is a sum of two complex exponential signals evaluated at the upper and lower limits, scaled by 1 over I omega. Using Euler's formula, we can see that this corresponds to a sine function. Because of the division by omega, this is actually a sinc function. I'm now going to show you an example. I will derive the diffraction limits using a Fourier transform of a rectangular function. The diffraction limit is a simple equation that provides a relationship between a wavelength, lambda, and an aperture diameter d, and an angular resolution, delta phi. Delta phi in this case means what is the smallest possible angle that you can resolve using an optical system, such as a microscope, a radiotelescope, or why not a human eye. The range of wavelengths that we can see with a human eye is approximately 400 to 700 nanometers. An eye is a very sophisticated optical system, but I'm going to make a lot of simplifications here. So this is a diagram of an eye. You've got the iris, which is the colored region, and then you have the black spot in the middle of your eye. This is called the pupil, and this is where light enters your eye. The aperture diameter of your eye is approximately the diameter of the pupil, and I have assumed it to be 5 millimeters. Using the diffraction limit equation, we can now estimate the smallest possible angle that we can resolve using a human eye. By plugging in the numbers, we obtain approximately 10 to minus 4 radians. A quick Google search indicates that this number is approximately in the correct ballpark. But the question remains, how does one obtain this diffraction limit equation? We're going to simplify things to a bare minimum. Here is a one-dimensional model for an optical aperture. I'm going to assume that this aperture has a diameter of d. That means that it extends on the x-axis from minus d over 2 to d over 2. This aperture is observing electromagnetic waves, or light, from different angles indicated by phi. I'm going to model light using the electric field of an electromagnetic wave coming from angle phi. The incoming electromagnetic wave is modeled using a plane wave. The blue lines indicate regions of constant phase. Now let's define distance r from the light source to the center of the aperture. This is the plane wave solution for a single spectral component of electromagnetic waves. Here, E naught of phi indicates the phase and amplitude of the electric field originating from direction phi, and e to I 2 pi over lambda times r indicates the phase progression of the propagating wave, and e to I omega t indicates the temporal fluctuations of this wave. We can get rid of the time variation by multiplying this with a negative frequency complex sinusoidal signal. Now we have simplified the electric field coming from direction phi as a one-dimensional complex sinusoidal signal. In this case, the independent variable is not t, it's r. Now let's investigate the phase and amplitude of the electromagnetic wave on the aperture. We've already defined what it is at the center of the aperture. Now we need to work out what the phase and amplitude is at position x on the aperture. By using the plane wave approximation and basic trigonometry, we can work out how much more distance the electromagnetic wave has to travel in order to reach position x. And now using the plane wave approximation, we can see what additional phase increment has to be added to the electromagnetic wave at position x. We're going to do one more approximation before we proceed. We're going to assume that sine of phi is very small. And now we have an expression for the electric field as a function of phi, r, and x. The last step of the derivation is to determine the sum of all electromagnetic waves from direction phi entering the aperture. We obtain this by integrating the electric field across the whole aperture. Using our previous result, the integral evaluates to this. We can move e to I 2 pi over lambda times r in front of the integral because it's a constant value. And what's left inside the integral is e to I 2 pi over lambda times x times phi. Now I'm going to set all of the constants in front of the integral as gamma, as what determines the angular resolution is inside the integral, not in front of it. Now you may already recognize this integral as the Fourier transform of a rectangular function. The only difference is that instead of a minus sign, we have a plus sign on the exponent. But this doesn't really matter, as I could have just as well defined phase progression as a function of distance with a negative sign. In this case, x corresponds to our standard time variable, and phi corresponds to our standard frequency variable. And this frequency variable is scaled by 2 pi over lambda. Using basic signal processing techniques, we know how to evaluate this integral and obtain a sinc function. So what does this equation tell us? It tells us what is the integrated electric field across the whole aperture from direction phi. We're just going to ignore the constant gamma because that's just the intensity of the light originating from direction phi. The sinc function is what the aperture does to this light. We can already see that if we increase the diameter of the aperture, we can make the sinc function become more narrow. That means that if you have a larger aperture, you have more resolution. You have more resolving capability. So at this point, my camera memory ran out, so I had to continue on another day. So this is the plot of the sinc function. Delta phi is the width of the main lobe of the sinc function. We can use the first zero crossings of the sinc function to estimate the width of the main lobe. Now this is the equation for the sinc function, which we just derived earlier, and we're looking for the zero crossing. We can find the zero crossing by inspecting the sine function. The argument of the sine function has to be pi, and the smallest non-zero value of phi naught is when phi naught is lambda over d. This means that the distance between the first zero crossings of the sinc function is 2 times lambda over d. And therefore, the half width of the main lobe is approximately lambda over d, which is the equation for the diffraction limit. This is also a good demonstration of the inverse relationship between the length of something in time domain and the length of something in frequency domain. If we increase d, then delta phi becomes smaller. I'll give you one more example of where you can use the diffraction limit equation. Radio astronomers often use radio telescopes distributed around the world to synthesize a large aperture the size of the Earth. Here's a map of radio telescopes around the world. These telescopes were networked together to form one large telescope with sufficient angular resolving capability so that it could be used to image the event horizon around the black hole in the center of the M87 galaxy. We can use our simple diffraction limit equation to study the angular resolution of this type of a radio telescope. The diameter of the aperture in this case can be up to twice the radius of Earth. And in the case of the black hole telescope, the wavelength that was used was 1 millimeter. We have now all of the numbers that we need to calculate the angular resolution of this type of a radio telescope. After plugging in the numbers, this is what we get: 7.85 times 10 to minus 11 radians. This is approximately 1,000,000 times better than the angular resolution of a human eye. Okay, so you may ask yourself, how can we do better? How can we increase the resolution of a radio telescope? Well, the obvious answer is to put a radio telescope into space. This way, the diameter of the aperture is determined by the distance between the spacecraft and the Earth. And therefore, the angular resolution of this type of a system is even better. Okay, that's the end of the video. I hope you enjoyed this real-world example of a case where you can apply the Fourier transform of a rectangle function.